Hello everyone. This is our second and last lecture for Chapter 6, Normal Probability Distributions. In this lecture video, we will introduce sampling distributions and the central limit theorem. The two most fundamental concepts of inferential statistics are 1. Sampling distributions, which are distributions of sample statistics like the mean, not of observations or raw scores. And 2, the central limit theorem, which allows us to find the probability of getting any specific sample and allows us to make inferences from samples about populations. Remember that the location of a raw score in a sample or in a population can be represented with a z-score. Researchers are more interested in studying whole samples rather than single scores. Samples provide us estimates of the population, but samples give us an incomplete picture of the population. There are aspects of the population that may not be included in a sample. The sampling error is the error between a sample statistic and the corresponding population parameter. It's the natural discrepancy found between samples and populations. Error does not mean a mistake was made. Samples vary. No two samples are identical. Samples differ from each other, and sample means differ from each other. Distributions in earlier chapters were distributions of sample scores. Now we will introduce the distribution of sample means, or sampling distribution. What is a sampling distribution? The sampling distribution of sample means, or sampling distribution for short, refers to the pattern of sample means that will occur as samples are drawn from the population at large. The sampling distribution of sample means presents all possible values for a sample statistic for a given sample size n. It is a theoretical probability distribution of the possible values of some sample statistic like the mean that would occur if we were to draw all possible samples of a fixed size from a given population. The sampling distribution allows us to determine whether, given the variability among all possible means, the one sample we've observed is a common outcome or an unusual outcome. For example, let's say I want to conduct a study to determine the number of miles the average person in Southern California drives a car in one day. It is not possible to measure the number of miles driven by every person in this population. So I randomly choose a sample of 100 people and record how far they have driven. I then randomly sample another 100 drivers in Southern California and record the same information. I do this a total of 5 times. I get the following results. My first sample of 100 drivers, the average miles driven per day were 15.9 miles. My second sample of 100 drivers, the average miles per day were 31.2 miles. Third sample of 100 drivers, the average miles were 27.3 miles. Fourth sample of 100 drivers, the average miles were 22.9 miles. And the fifth sample of 100 drivers, the average miles were 24.8 miles. Each sample has its own mean value, and each value is different. If we could continue this study by selecting and measuring all of the possible samples of n equal to 100 and observe the pattern of sample means, this pattern of sample means represents the sampling distribution for the number of miles the average person in Southern California drives. This distribution is the sampling distribution of sample means because the mean of each sample is our measurement of interest. By taking a sample from a population, we don't know whether the sample mean reflects the population mean. From the sampling distribution, we can calculate the probability of a particular sample mean. Chances are that our observed sample mean comes from the middle of the true sampling distribution. The sampling distribution of sample means has a mean and standard deviation just like other distributions we've talked about. The mean of the sampling distribution always equals the mean of the population. Your textbook uses mu x bar for mean of the sampling distribution. It is also mu m, capital M. So mu m is equal to mu, or the mean of the sampling distribution is equal to the mean of the population. The variability of the sampling distribution is called the standard error of the mean, or SCM for short. Think of the standard error of the mean as the standard deviation for sampling distributions. The standard error of the mean measures the variability in the sampling distribution. It roughly represents the average distance that sample means are away from the mean of the sampling distribution. Standard error of the mean is equal to standard deviation divided by the square root of n. Also equals variance divided by n. Now let's talk about the central limit theorem. If the sample size n is sufficiently large, the shape of the sampling distribution approaches a normal distribution, regardless of the shape of the actual population. The sampling distribution of sample means is a more normal distribution than a distribution of raw scores, even if the actual population is not normal. The central limit theorem states the following. The sampling distribution approaches a normal distribution as sample size n increases to infinity. If sample size is greater than or equal to 30, the sampling distribution can be considered normal. If sample size n is less than 30, the sampling distribution is normal only if the raw score population is also normal. The mean of the sampling distribution is always equal to the population mean. The sampling distribution will have a standard deviation called standard error of the mean, and there's the formula. Sigma m is equal to sigma divided by the square root of n. How do we use the central limit theorem? If we know that the sample means follow the normal probability distribution, and we can calculate the mean and standard deviations for that distribution, we can predict the likelihood that the sample means will be more or less than certain values. We can actually calculate z-scores to determine this likelihood or probability using the standard normal table. The Z formula for sampling distributions is the sample mean minus the population mean divided by standard error. Remember that standard error is the population standard deviation divided by the square root of n. I have posted videos from Khan Academy that will walk you through how to solve for probabilities using the standard normal table. Let me know if you have any questions. This concludes our coverage for Chapter 6.